Morning. Let me go to the details of what we have done in the previous lecture, that is the lecture 6. That is precisely we discussed much on the elaboration of what we have done on the general equilibrium, and in this particular paper, what in this particular lecture, what I am trying to do is an equilibrium analysis, which is generalized Walrasian case, that is Walras Wald. Walras Cassel model to that of the Arrow-Debreu model, which is actually the very important aspect of the general equilibrium understanding of the modern times. So, to begin with, let us go to the nitty-gritties later. But this is the same mechanism which we have already covered, but a slightly different understanding. A general introduction to make such an equilibrium is the following: that is, we have to have a discussion on a Walras Cassel model, and then we discuss about Wald correction, and then we move on the Arrow-Debreu model. Okay, to make it more interesting as well as convenient to basically understand. So on the complexity of equilibrium and all would be the last portion of the same. So we, as a setting stage, we have already discussed about the general equilibrium of general kind, which is normally in the undergraduate level used to teach and all. So what is the problem with the general understanding of the general equilibrium or Walrasian kind? That is, individual are endowed with factors like labor, capital, raw materials, and they demand produce goods. Firm demands factor and produce goods with a fixed production technology. And the question is that if that is the case, does general equilibrium exist? So, what does this realistically tell us? What this particular kind of understanding realistically talk about? As on the competitive market is also we have seen. So in the Walras Cassel model discuss about where market demand is equal to market supply in all markets. That is the factor, and goods marketing is actually in equilibrium and maximizes utility for each consumer, and firms maximizes the profit. In notation terms, we can see that this model represents in terms of the household and the firm in produced commodities in primary factors. And produced commodities which is actually the household X vector, that vector commodity demand by the household, or XF is actually the vector of commodity supplied by the firm F. And P is of course the positive vectors of the commodity price in that sense. And you have factors such as VH, that is the vector of factor supplied by the household, and vector is actually of factor demand by the firm F. W is again the vector of different prices. And technology, we always talk about technology, but in this particular case, a fixed proportion of technology, the same tech in all the firms. That is the strict assumption. In fact, this follows, and if that is the case, then the Bji, which is equal to Bjf of xi, is what is actually normally being seen as the coefficient, and B is actually an xm matrix of unit input coefficient. So once you have all this thing, then the unit of output production coefficient is also be given, and then it represents the amount of factor J which is necessary to produce a unit of output I. So this is what is actually the notation roughly speaks about. J is actually the necessary produce of that is the factor, and I is actually the output. And once you have all, capital B is actually the Mn matrix of unit output coefficient, so that you have an inverse V that is minus P, which is equal to Bx, where vector x is the supply of produced goods, and V is actually the demand for factors. Now once you have all the setting, then we can see everything in the perfect competition scenario, as we have discussed earlier, the simple Walrasian case which we have looked into. So once you have that, then the perfect competition scenario, entrepreneur make no positive profit or no losses. In this case, we have discussed this is from the first semester onwards, and total revenue of PXF, which is equal to the total cost of WVF for every firm F, or what you call P dash Fx, which is equal to W dash VF, or as Bji, which is equal to the other vector which we discussed, that is Bji, which is equal to Bjf of by the xif. Then the perfect competition assumption imply that your P is equal to Bw. Now, once you have all this thing in place, then the households and the household's objective or the consumer's object is being clear to maximize utility. That is UH from X and Y, which is households utility, which is being maximized from the commodity consumed, that is X and B. So utility increases with consumption produced commodities of X and utility decreases the supply of factor VH. Given an amount of set of prices, that is PV, the household H households maximization of utilities the following: like you have UH, that is the utility of household, which is equal to UH of XH VH, such that your P dash XH, which is less than or equal to W dash VH. That is the now the point is the consumer cannot have more than what they can or they requires, the selling factor or W dash VH. This is actually a complete equilibrium model in that sense. A result of the budget constraint, we can derive a set of output demand function and a factor supply function of the following general form is another part of the same problem, that is the resulting function of the same issue. That is, you have an xi which is equal to di pw for each commodity I to 1 to n, I which is equal to 1 to n. So you have also an inverse pj which is fj pw for each commodity j which is equal to 1 to n. Okay, now once you have this utility function, and now you have a utility objective function, and then you have the commodity cases, and then once you have all this thing, then the market clearing function can be discussed very simply, that supply must meet demand more explicitly, which is both of EH XIH, which is equal to summation, sorry, not EX, sorry, it is a summation of H XIH, which is equal to summation of X XI F for each commodity I to I, which is 1 to N. That is, there is an individual if that is the case. So, or in the case HVIH, which is equal to summation of HVIF for each factor j, which is equal to 1 to m individual. So we, given our earlier notation, this can be rewritten as di pw which is equal to xi and fj pw which is equal to bj, which is nothing but the b dash x bj dash x. Okay. Now, if you remember all the previous equation, which is the perfect competitive equation, where you pi which is equal to piw and output market equilibrium is di pw which is equal to xi, and factor market equilibrium is vj bj dash x, and the market factor supply which is fj pw which is equal to Vj. So if you know this thing and the things are very pretty clear, Vj is equal to this one, that is the factor market, which is also the market factor supplies, and the other one is also very important. So once you have this thing, then the perfect competition case, you have this particular diagram and be the result of that assumption, which is you have a supply and you have dpw, which is nothing but output market equilibrium, and you have a p which is p star which is equal to p bw star, which is nothing but this one. Okay, perfect competitive equilibrium, or the ideal factor, as well as the x as well as the w combination. So these are supposed to be a vector. That is the first caveat one who can actually point from this particular model is that uh, these are vectors. Okay, vector is actually a unidirectional kind of a relation. Then the output demand function is also function of w, and the factor demand function is also function of p. So there is an interaction between the diagram which will cause the curve to shift around. So this is actually the kind of a caveat which you can observe from the very preliminary observation of the kind. So if you think about equilibrium, then there are proofs we have already discussed, that is your per competition case, output market case, and factor market equilibrium and market factor supplies. So you have four equations in that sense, and you have four unknown xi, vj, pi, as well as wj in that sense. Now, once this is the case, then if you for market, then in the beginning I said, you can 1 minus the equation can also solve the thing. This immediately props from this particular understanding. So I'll come to that later. So once you have all this n unknowns, m unknowns, n unknowns, and m unknowns, then you have an n equation, and case, which we have already discussed. So there, if it is an equilibrium, then you must have only one solution in that sense. So you may be having two equilibrium, two equation and two unknowns, but the equilibrium one is actually a single point in that sense. So the proof of that particular case is there are 2n plus 2m equation and 2n plus 2m unknowns. So this must be a solvable set of equation prima facie, and the problem xi which is equal to 3 and x plus y which is equal to 1 has no real solution in that case. So in the context I have only one factor and two factors such that p is equal to b1 w1 plus b2 w2 has no solution, since there are numerous combination of w1 and w2 that can yield the same output price. So this is what is actually the kind of proof in that context, with the imposition of equalities, which is equal to b dash x and p is equal to wb, prices may turn out to be negative in that context. And while negative prices, the quantities are completely feasible, they mean nothing in this context. Okay, that is the problem with this understanding. Again, this problem is immediately fixed by Wald, and that is what is called Wald's fixing. So the idea of free good, all factors are scarce and thus all have a price. However, factor is scarce only if there is more demand if than is available. But if supply far exceeds the demand, the factor should have a zero price in that sense. And real life example, tap water, air, internet, etc. can be used as an example of this thing. And Carl Menger had a critical point, that is, one does not know at the outset which good are free goods, so one should insert into the equality the possession of an unused residual in that context. So this is also a very interesting observation made by Carl Menger. The problem was, if introduced inequalities is existing of the equilibrium certain, it's a question normally posed. In that context, if you have a Vj which is greater than or equal to Bj dash x, in equilibrium for a particular factor j, either the quantity supplies is equal to the quantity demand. That is, when you have a Vj which is equal to Bj dash x, or the quantity of the factor supply exceeds the demand for the factor Vj, which is greater than Vj dash xj. X, but then the corresponding return to factor j must be 0, that is wj, which is equal to 0. That is one kind of understanding. And then you also have a problem with the primal vis-a-vis dual proof of the existence, and in that is also pretty interesting in that sense. So if you have a primal issue that is maximized with p dash x, output revenue such that you have a b which is greater than or equal to b dash x, where your x is greater than or equal to 0, where dual means the minimization w dash v, that is factor paid, such that you have a p which is less than or equal to pw, and the w is greater than or equal to 0 in that context. So you have actually the opposite, which is what is called the primal dual case. I don't want to go to the details of that. And other constraints was that we need to make sure cost of production pw did not fall below output price. If it does this, if this does, then the company wouldn't produce it. In other words, xi which is equal to 0. So it is quite clear in that context. Then if we apply this as in a duality theory of a linear programming model, things maybe looks not so different, but yeah, we can understand in a simple way. There exists a solution to the primal, that is x star, if and only if there exists a solution to the dual w star. This is an immediate kind of a deduction one can basically arrive at, and the maximized value, the objective of a primal and a dual are the same. Therefore, in our case, that means p dash x star, which is equal to w star v dash, which is another way of imposing pure competition at an equilibrium in that context. So again, if we again look into the same issue in a Lagrangian multiplier case, which satisfies the primal problem, is the solution vector to the dual. That is, you have a lambda star which is equal to w star, and the multiplier which solves the second problem is solution vector in the primal. That is, you have a mu star which is equal to x star, implies that the equilibrium w star, which is v minus b dash x star, which is equal to 0, where you have an x star inverse bw minus p, which is going to be 0. This is what is actually we had sufficiently discussed, set grounds for all this Lagrangian multiplier case in an extensive form in the first semester. So I have to move a little further. In case of any doubts, we will discuss about all that in the subsequent lecture. And we also need to basically keep in mind that you have also complementary slackness condition exist, and if that is the case, there are important B by C case, that is, they replaces the condition for equilibrium and allow for free goods. If that is the case, then you have this W star V minus B dash X star, which is equal to 0. Either it turns either V is equal to B dash X star, factor market equilibrium, or if there is an excess of factor Vj which is greater than Bj dash X star, then you have a Wj which is equal to 0. The factor is here free. Thus Wj star is greater than 0 only when Vj is actually equal to Bj dash X star. That is, a factor earns a positive return only if the market for that factor clears. So this is a very interesting deduction, which is in fact we have already discussed, but in a very nuanced sense. It is a nice way of putting it up. So in the inverse x w, same the case with the w star. If you look into the x star case, that is bw minus p, which is equal to 0, same as above, except every produced good must equal its cost of production. All right. So this is what is actually the idea. But the proof I will be discussing in the subsequent next lecture, because otherwise the lectures gets a little bit lengthier. So let me stop here, and I'll come with the Wald's proof in the coming lecture. Thank you for listening.